So another type of problem that can be tricky are circular motion problems. So let's consider this problem where we have a crankshaft in a race car, and the crankshaft is going from rest and goes up to 3,000 RPM in 2 seconds. So we're asked how many revolutions does it make in this time? So the first thing that we're going to want to do is we really need to unwrap the circle. Unwrap the circular motion. We can treat circular motion just like we have one-dimensional motion in a straight line with acceleration. And so that's going to be our approach. So we'll draw a line like we had before, kind of pretending as if this thing was moving in a line with an initial and a final state. And so let's say it starts at 0 radians, and we do the same approach that we do with one-dimensional motion. We label the initial and the final. Everything we know about the initial, everything we know about the final, and everything we know about in between as well. So initially it starts at 0 angle radians, 0 seconds, and 0 radians per second. At the end, it's moving at some final angular velocity, which we don't really know at the moment. It has some final angular position, which we're actually wanting to find. And this takes 2 seconds to get here. And during this time, we expect there must be some angular acceleration to the right as we've drawn it. So let's just quickly list the things we know and things we don't know from this. So known and unknown. So we know everything about the initial. So we know theta I, Ti, omega I. We know the final time. We know the final frequency. So I'm going to put that as f sub f, final frequency. What we don't know is we don't know this final angular speed yet. We don't know the angular acceleration alpha, and we don't know the final angular position. And the final angular position is what we're ultimately after. So let's, before we go too much further, let's write the final angular speed. So the final angular speed should be 2 pi times the final angular frequency, this f sub f. So that's 2 pi times the final frequency we had as 3,000 revolutions per minute. And we want to convert the revolutions per minute into revolutions per second. So we have to have 1 minute is equal to 60 seconds there. And once we multiply all of that out, we should get something like 314 radians per second for omega f. So now we've actually moved this final angular frequency, final angular speed, omega f, over to the known category. Okay, so now we have what we know. The things we don't know are alpha and theta f. And so as you might suspect, we're probably going to have to solve for alpha first. And we can do that by using this expression, the final angular speed is equal to the initial angular speed plus angular acceleration times change in time. So that the angular acceleration is this. And that gives us something that looks like 157 radians per second squared. Now, just to note, this is positive. So this means it's to the right, as we've drawn it. And that matches what we had in our picture. The angular acceleration was pointing to the right. It was speeding the crankshaft up. Okay, so now that we have the angular acceleration, and we want to find the angular position, so we're going to use the expression delta theta is omega I delta t plus 1/2 alpha delta t squared. Of course, we could use the other equation as well, but this one ends up being a little easier. Now the initial angular speed is 0, and so this simplifies to be that the change in the angular position is just 1/2 the angular acceleration times change in time squared. And so we multiply this out and we get 314 radians. Now the question asks how many revolutions does the crankshaft make, not just radians, and so we need to convert this into revolutions. And so we do that by noticing one revolution has 2 pi radians. And so multiplying that out, we get somewhere around 50 revolutions that the crankshaft makes. So again, the approach to solving these one-dimensional circular motion problems is to make them look like a one-dimensional motion problem and solve them using one of those 3 major equations, as we did in one-dimensional motion.